same schedule, more or less.
Wir sind bereit.
Drei, zwei, eins, Start.
Very good morning, ladies and gentlemen from Cologne in Germany. A very warm welcome to our FOGTEC webinar on water mist systems in tunnels. Today our presenters will be my colleague Tim Usner. He will give an overview about the new Carey tunnel refurbishment in New York City, and myself, I will give an overview about the company, the background of water mist systems in tunnels, and some ideas on compensation potential. A quick introduction to ourselves. I've been working for FOGTEC for almost 10 years. I like to travel, enjoy life. Tim is a fire protection engineer from Cologne. He has a very old camper van, 20 years, which takes a lot of his spare times, which he enjoys a lot. So before we come into the details of today's topic, we are very happy to receive your questions, which we will answer at the end of the session. You will find a question bar on the side of your screen, shown here in the window. use the question panel to ask questions. As I said, Tim and myself will answer these questions at the end of the session. Please do not hesitate to use them as much as possible. Now, today's agenda will look like the following. A short introduction to water mist systems in tunnels, company introduction. Tim will present the latest case study of the Carey tunnel in New York City, very interesting refurbishment project. And then we will conclude with some compensation potential, some of our experiences of these systems in tunnels. FOGTEC is an owner-managed company. We're in the market for almost 25 years. We offer a very wide range of supply and engineering services. We are market leader for water mist systems in tunnels. We have additional offices in India and in China, and our business units are the fixed systems, so all kind of building and application, building and industrial units. Thank you, Tim. Railway systems, tunnel systems that we're talking today, and new energy carriers, so everything which is related to fire hazards with batteries and the like. Some of our customers, a selection of references. You might know most of these companies, very prestigious references throughout the world. I don't want to go into detail, but let you have a look on our experiences here. We are, moreover, very active in guideline work, research projects. Me, for example, I'm sitting in the technical committee of NFPA 502 as an alternate to our managing director. We are part of NFPA 750, ITA course of various research projects you might have heard of. So long-range experience with all these topics here. Just to give an idea of our system, how water mist system in tunnel typically looks like. Normally we have a pump station supplying the water, supplying the pressure through a main pipe, which is typically filled with water all the time. During activation, three water mist sections will be opened. So around 70, 80, 90 meters total activation length we will have in the tunnel. The system consists of the pump station, water tank, typically stainless steel pipework, section valves, water mist nozzles distributing the water, a control system to activate and control the system during activation. Reliable components, a simple setup, that's definitely a key to a good system, a life safety system, a fire safety system. The principal activation looks like the following. So you have an incident in the tunnel. The alarm is being set off by a CCTV or LHD system. The operator or the system will start the pumps immediately, putting up the pressure, supplying the water throughout the pipework. Three section valves will be opened in order to be able to encapsulate the fire. And in around about 60 seconds, we will have the full flow rate distributed inside the tunnel to fight the fire immediately. These systems have been fire tested in many fire tests. So we've been doing this for probably around 25 years already, as you can see in the list. More than 200 of these tests have been conducted in test tunnels for Class A and Class B fire loads. We have also tested battery fires lately. Heat release rates of more than 200 megawatt have been tested, and we have carried out these tests with ventilation speeds in excess of 5 meters per second, so very high wind speeds inside the tunnel. Just a quick idea on temperature graphs from fire tests. On the upper side, we see a Class B fire of 100 megawatt size. We can see a very sharp rise in temperature, and upon activation, a strong decline in the temperature. So these measurements were taken 5 meters downstream. And if you have a more detailed look, you can see that the temperatures are controlled to around 50 degrees Celsius, just 5 meters beyond the fire load. On the lower end, you'll see a Class A fire, 150 megawatt, measured 15-meter downstream. So very similar temperatures, very low temperatures inside the tunnel. Definitely a key success of these systems. To conclude the first part of my presentation, we can see that the water mist system is able to really lower the heat release rate in the tunnel, as you can see in this graph here. We have an immediate cooling effect after activation. We efficiently protect the tunnel structure. We are able to reduce the amount of smoke in the tunnel significantly, fighting the fire, controlling the fire, providing life safety to tunnel users and to firefighters, so being able to escape, being able to enter the tunnel to fight the fire, extinguish the fire, provide high availability of the tunnel and infrastructure, and as mentioned before, very active for Class A and Class B fire loads inside the tunnel. So I will now hand over the word to Tim to give some overview and show some pictures about the latest interesting case study in New York City, the Carey tunnel.
Hi everyone. My colleague already introduced me shortly. My name is Tim. I'm working as a sales engineer for FOGTEC, and I'm also the project manager on the FOGTEC side for the case study which I'm going to present you today. The project is called the Carey tunnel. It's a fairly old tunnel which was opened in 1950, and it's about 2.8 kilometers long, and it connects the Manhattan Island with Brooklyn, which you see down below here. It is formerly known as the Brooklyn Battery Tunnel. That may be the name you might heard in the past, but it was renamed a couple of years ago. And it got a design fire load of about 30 megawatts. And it also has a fully transversal ventilation system. That means we have an exhaust air duct here on the top, and fresh air duct below the street itself, and throughout the tunnel itself, several exhaust blower buildings. It's also a tolled tunnel, which means you have to pay to drive through it. It's around about $10 and 50,000 vehicles per day drive through this tunnel. So it's also the first water mist system inside a tunnel in the USA. And when we are coming to the reasons why they have chosen to retrofit this tunnel with a water mist system in the first place, is that they had a car fire several years ago, and this is when the first apprehensions in regard to fire risk came up, and the authority having jurisdiction in New York City, they thought about retrofit possibilities in order to, say, prevent major damages, especially on the fans throughout the tunnel, because the hot gases, which will then go through these exhaust air ducts, these hot gases, they are passing the fans. And some major components of these fans, they are not suitable for very high temperatures. So they have looked for possibilities to get a cooling effect and to reduce the heat release rate. And that's why they have chosen a water mist system in the first place. So what was also asked is to get all the components outside of the tunnel. So all of the components for the water mist system. That means the main pipe, section pipework, section valve, everything needs to be placed inside this exhaust air duct. As we are having, or as we can take high pressure losses into account, we've got small pipeworks and small system components, which means that it's quite a space-saving technology. So the only thing which will then lead into the tunnel are the nozzles, and they will be placed through these exhaust vent openings, let's call them. You can see them here on this picture below. And this is where the nozzles will then be placed inside the tunnel itself to get the water mist system then sprayed here. As we only need a limited amount of water for a fixed firefighting system, it also had positive side effects of the drainage. As it is a retrofit project, an adaptation of the drainage was not needed. So that's quite beneficial for the end client as it is cost saving. So to sum it up, due to the small components, it's quite easy to retrofit it into an existing tunnel. Before the installation started, a spray test was asked with a positive outcome. So the reason for this test was that no major mist suction into the exhaust duct was allowed. It was tested with a mock-up, so let's say a sample installation, and the emergency ventilation mode was turned on with about 3 or 4 meters per second, I think. After that, the water mist system was activated, and then it was observed that no major spray pattern was lost into the plenum. So the outcome was that even with the emergency ventilation on, the exhaust duct or the vent openings, they do not have any effect on the water mist system itself. We had a research project in the past called SOLID, where we have also tested the temperatures inside the air duct in the test tunnel. So as you can see here, these 2 blue lines, they are thermocouples, which we place inside the air duct about 100 meters downstream of a 150 megawatt fire. So that's 5 times the size of the design fire load for the Carey tunnel. The red line you see here is the activation of the water mist. And as you can see on this chart, after activation of the water mist system, the temperature inside the air duct was kept below 40 degrees Celsius. So we also used these starters in order to, let's say, show that we can prevent high temperatures with an activated water mist system. If we are coming to some challenges which have occurred during the project itself, let's say, the space to get inside the air duct is quite narrow. As you can see here, this hatch, these are the only places where you can get the components inside the air duct. So you can imagine having these space-saving components, which we have, is quite beneficial here in order to get everything inside the air duct and then for installation. These 2 pictures are pictures taken inside the air duct themselves. And the installation was done or is still done under partial closure. And yeah, as you all know, due to the COVID pandemic, we had to do remote execution of the project. So we did not fly over to the US until now, which worked out quite well. We even did our first purely online factory acceptance test as a video conference. So this was new for us as well. But it worked out quite good. We did a video conference with the consultant, with the end client, with our client, and yeah, they were quite happy with the outcome. As you can imagine, space is quite limited in New York City, especially in Manhattan itself. So the pump room is placed here at the Manhattan blower building. Only very limited space was available to do so. So that water mist system needs only little water storage comes in hand here. Also, only 1 pump station is needed. The system needed to be full-scale fire tested. That's what the end client asked for. As we have experiences with over 200 fire tests, no additional tests were needed. So that means we didn't have to carry out any additional full-scale fire tests, which is time and cost saving. And we were able to took our own data, and then an institute in Berlin called IFAB, they took these data, which we had from previous fire tests, after adapting it to the parameters of the Carey tunnel. It came out that the fire tests were, or we could reuse them, let's say, so no additional tests were needed. Also quite beneficial was that the nozzle layout, it perfectly matches the distances of the ducts. So we can place all these nozzles through these ducts without any adaptation needed, which is also quite beneficial. Implementation at the moment is ongoing. The installation inside the air duct is also still ongoing. The pump room the civil works for the pump room, they have started and they're about to get finished, and we will have a full completion of the project within still this year. And the prefabrication of the pipework, it's happening parallel to the installation works. Stainless steel main pipe is used, which is connected by welding, which means quite a robust and long lifetime for this pipe. And the rest of the section pipe work is done with fittings, which means that it's quite a fast installation inside this air duct. All the components for control of the valves were or are placed inside the fire protection box. So we are placing our valves inside the fire protection box, as it is the only active component inside the tunnel, or in this case inside the air duct. So it's prevented from damaging, and 2 valves per fire protection box due to fires or due to space saving reasons. Right now, the final installations inside the exhaust ducts are happening. The last section valves and fire protection boxes are going to be installed. And also some signage tests are done, because they are activating the system fully remotely, the operators. And so the signage tests, they were done in order to see through the CCTV which zones need to be activated. So these tests are still ongoing, and only for, I think, 2 or 3 sections, the exhaust vent distances did not quite match the nozzle parameter, and their core drillings needed to be done. But as we proposed a quite flexible solution with flexible hoses, the adaptation was fairly quickly done. Impressions on the current status. This is the brake tank, which is going to be installed inside the pump room itself. Another picture of the signage tests which are happening at the moment. This is the pumps which are delivered on site. So in order to be space saving, we decided to stack these pumps, as you can see over here. This is how they are placed, as well as our control and power cabinets for the pump room itself. And this is how our components look covered inside the pump room, which I've shown earlier. So what are your takeaways for this short study for the UL Carey tunnel? Water mist system seems to be an excellent solution for this retrofit project. It is full-scale fire tested, which means no additional tests needed to be done. And it is easy to retrofit into an old tunnel. Also a space-saving technology. The complete remote teamwork with the client went very well, despite COVID-19, and we didn't have any major delivery problems. So as I said, the layout of the fire test matched the exhaust ducts distances quite well, and compensation with the water mist system worked because the ventilation system itself had only got a refurbishment and not a replacement, which is faster and also cost saving. So we also raised the availability inside the tunnel, because it can get reopened more quickly with the water mist system. As you saw on my first slides, we have about 50,000 vehicles per day, and as you can imagine, a closed tunnel for several weeks inside New York City means some chaos, to be honest. And no major tunnel closures for the installations were needed. And with this being said, I would like to get to the next part of our webinar, and I'm giving back to my colleague Armin, and I'm happy for your questions, which we will answer at the end. Thank you.
Thank you very much, Tim, for the interesting presentation on the latest project. Definitely a very nice case study, which is being completed very shortly. I will now conclude with some ideas on compensation potential when using water mist systems in tunnels. First example, ventilation systems. So You can see some images on the lower right of the slide from a test tunnel in Spain. This test tunnel has a ventilation system which is designed for a size of only 30 megawatt. Now, we have done a fire test with 100 megawatt in this picture, and you can see that before system activation, we had a significant backlayering in the tunnel. So the ventilation system was not able to push the smoke downstream of the fire, so it was not able to keep the upstream side clear of smoke. This is obviously very critical for tunnel users and fire safety services. So this is something we definitely want to prevent in case of such a fire. Upon activation of the system, we have suppressed the heat release rate. You can see this in the slide. And you can also see that the smoke amount was then obviously reduced. The upstream side of the fire was clear of smoke, so providing a safe area for fire services and for tunnel users, and no backlayering was observed after activation of the system. Which means that a full-scale tested water mist system is able to compensate the ventilation system or partly of the ventilation system of the tunnel. So with a 30 megawatt ventilation system design size, we were able to manage a 100 megawatt fire suppressed with a water mist system. So we can increase the performance of the ventilation system using water mist systems, allowing to save costs, and as we have seen also in the New York City tunnel project, a very good option to refurbish your tunnel. Coming to the structure protection, probably one of the main requirements why water mist systems are being installed into tunnels. Water mist systems shall protect the structure of your tunnel from high temperatures, prevent the spalling of concrete, protect your asset in case you collect toll, secure your toll income of the tunnel, and obviously increase and secure the availability of your tunnel and the overall critical infrastructure for the society. Now, we have also tested the structure protection scenario for water mist systems. You can see we have prepared a brick, a concrete brick. We have put sensors in different layers into these concrete brick. We have placed the brick just above the mock-up of the fire tests. And obviously we have carried out the fire test then to see and collect the temperatures with a water mist system and a severe truck fire in the tunnel. We have seen that the critical values were not reached, so temperatures at the ceiling were kept below the critical values for the reinforcement of the tunnel. Then we can also see that only a very small area was exposed to high temperatures. We did not have a truck entirely burning, we did not have a spillover to adjacent vehicles. And we saw that we did not have any damages, any major damages, nothing severe at the tunnel structure, meaning that the water mist system was able to prevent the spalling and to prevent damages in the tunnel structure. We have seen on the next slide that the critical temperatures were not reached. Only 315 degrees Celsius for a very short period of time was reached at the peak. So concluding, we can say that the passive protection measures can be compensated by using a water mist system. We are able also to protect the rest of the M&E equipment inside the tunnel, cameras, lightning, detection systems, whatever, and that the system, a quick activation of the system also allows to reopen your tunnel very quickly after a fire incident. We had a few cases or there's a few reference cases where water mist systems or fixed firefighting systems have been used in tunnels. The Dartford tunnel in July 2016 was subject to a fire. A small car was burning. You can see in the back a picture from the social media. The water mist system was activated. We can see that the upstream side of the tunnel is clear of smoke, and the tunnel could be reopened just 82 minutes after the fire was activated. So very quick reopening, very quick availability of the tunnel for the society. 2 months later, similar incident, again a fire in the tunnel. We can see also again in the back on the right picture the activated water mist system. So we have seen the fire suppression system, the water mist system was activated, everything worked according to protocol, and the tunnel was opened just 1 hour and 23 minutes after the fire has occurred. So again, very efficient protection and high availability for the infrastructure. 2 more examples of successful uses of fire suppression systems. Many of you might know the Burnley Tunnel fire, a major fire incident. However, it was a deluge system in this case, suppressed the fire, it prevented the fire spread to adjacent vehicles, and the tunnel closure was very limited despite, let's say, a major fire in the tunnel. So after a few days, the tunnel was open again. Another case, a water mist system in the Arlberg Tunnel, again, a major truck fire had happened, the system was activated, no tunnel damage was recorded, and the tunnel could be opened within just 2 hours of a severe truck fire in a tunnel. So we can conclude and say that the water mist system is able to extend or improve the availability of the tunnel. We can allow a quick reopening even after a severe fire. We allow for a very limited cost impact only in case of such an incident for operators, for society, no long-term traffic deviations, minimizing costs for tunnel repairs. In some cases, we didn't have any tunnel repairs costs. Very minor or no impact to the economy. So keeping the transport availability up, opportunity costs very low, almost no loss in time. Then reduction of insurance costs, in case the tunnel is insured, and of course securing toll incomes for operators. So with this slide, I want to conclude our webinar for today. We are very happy to receive your questions and feedbacks. We're happy to discuss about tunnel projects with you, and I will now call also my colleague Tim to come back into the picture. So we want to go through the questions which have been raised. Thank you for listening so far, and I will just have a look the questions which have been raised here. One audience is asking whether we have any data on the amount of evaporation that could be expected in a 50 megawatt fire for a system that has used 3,250 liters per minute being discharged across 3 zones. It's a bit difficult to give a flat rate value. It really depends on the fire size, on the fire type. We will have a look to the fire test data, whether we have any recordings or calculations on the evaporation, and we will come back to you later. Otherwise, have a look at www.solid.info. You can find a number of reports and information publicly available from these kind of fire tests.
I think I will take on the next questions if you're finished with this one, because I think they are regarding the Carey tunnel. So one of the questions is, what was the length of the NYC tunnel? It's about 2.8 kilometers, and it's got 2 bores. And the first at the portals, it's a cut and cover, and then it's a bored tunnel. And the next question is if the valves were also installed inside the air duct. Yes, they were. And as I've shown on one slide, they were then also placed inside a fire protection box themselves. Another question is if the high wind speed did have any effect on the performance of the water mist system. That's what the let's say first spray test was for. And of course, with the let's say activated ventilation system, you have a slight offset of about, I don't know, let's say 1 or 2 meters. But as we are always activating 3 zones, it does not have any effect on the firefighting capabilities.
A small offset we see, but nothing major. We have seen the same effect also for deluge systems, in fact, in the tower tests.
Yeah, and also so inside the air duct, as we were able to see on the pictures, there were no water inside the air duct because of the activated ventilation system. So.
Okay, so another question, whether it's possible to get the report of IFAB for the tunnel in New York. In fact, this is obviously subject to our end client, whether he's willing to share the report. Typically, they are kept confidential for internal reasons, so it's not in our hand. However, the report, let's say to give a quick overview or quick idea, the report checks the fire tests, set up the fire test performance, and compares whether the fire test requirements for the UL Carey tunnel have been met by the fire tests. Yeah? And the report concludes that yes, the setup of the water mist system in the tunnel in New York is, let's say, the same or better as it was during a fire test. So meaning that the system is able to work also perfectly in the UL Carey tunnel. Another question, whether the regulation in New York City requires installation of fixed water suppression systems in rail or road tunnels, whether NFPA 130 or 502 requires that or not. No, there is no requirement to install such a system into a New York City tunnel. So this was kind of a case-by-case analysis. And the outcome was that the water mist system is a very good solution to upgrade and protect the tunnel in New York City. So it's no requirement by law or by regulations here.
However, NFPA 502 has its own chapter about fixed firefighting systems, describes the benefits and compensation potential of these systems.
Correct. One more question regarding the number of nozzles in one zone and density design ranges as per past tunnel project. I mean, the number of nozzles really depends on the zone length, of the size of the zone, of the height of the tunnel. So we really need to adapt the design of the system to each and every project to be able to meet the minimum requirements according to the fire tests. Typically, we can say that the distance of the nozzles is somewhere between 2 and 5 meters. Really depends on the tunnel and the design, but this is kind of a rough indication of the zoning of the nozzle layout. Question: if we had installed the system into a new tunnel? Yes, we did. A couple of new tunnels, we did the installation. So currently ongoing in 2 tunnels in Egypt. The water mist system is being installed. New tunnels. The New Tyne tunnel, one of the New Tyne tunnels was new during installation. We had 2 tunnels in UAE where the system was installed into new tunnels. So yes, it's used for old and for new tunnels likewise. So very good refurbishment possibility. When having a new tunnel, of course, that allows you to really compensate also existing deficits or reduce the costs using such a system here.
Also, the earlier we get involved into a new build tunnel, let's say, the better, because we can improve how to implement it. And
yeah, absolutely, very correct. A question: how big were the pumps associated with the New York tunnel? So we had a pump set consisting of multiple pumps and 1 redundant pump. So there's always a redundant pump in the system. In case that 1 pump would fail, the redundant pump would kick in. Question: whether there's any example of water mist systems used in rail tunnels? Yes, there is. We have actually installed a system into the Eurotunnel. This is now in operation for around 10 years. We did major fire tests for that project. The catenary line was also tested. Another question related to electric lines here. So typically we recommend to cut off the power from the catenary lines before activation, but the system has also worked with the catenary being on power. without any side effects or any flashover.
I think there's also a video on our YouTube channel which shows the activation inside the Eurotunnel with a catenary turned on, so you might check this out as well.
Yeah, have a look to our YouTube channel. You can find some videos in addition here. A question whether we can also show data for 200 megawatt and the effect of water mist, not only 100 and 150 megawatt. So yes, we have conducted 200 megawatt fire tests, even above 200 megawatt. There's some limited information available. The report is subject to a client, so we are not able to share the full fire test report. But again, have a look at our YouTube channel, and if there's, let's say, detailed questions, we might be able to answer some of the questions or all of the questions to you directly. So please just come back to us by email or give a call afterwards.
Yeah, but to sum it up, we have tested it even above 200 megawatt and would be able to fight these fire scenarios as well.
Yes, we did. One last question we want to answer for today. The influence of the system on the speed of the ventilation system flow. We have, as I said, we are always testing the systems with activated ventilation as per requirements for the tests. We have actually tested, I think, up to 7 meters per second in the top speeds. Typically, the ventilation speed is somewhere around 3.5 meters per second in the tunnel. There is a minor effect of the ventilation to the water mist. So we see a very slight offset of a few meters. Having said that, protecting, for example, 75 meters of tunnel length with water mist does not have a major effect. The water mist systems have worked perfectly in combination. The ventilation system has worked perfectly in combination with the water mist systems. And this is also common practice in many countries and many tunnels where this has been installed.
I think the question was meant the other way around. If our activated system is having some effects.
Yeah, I mean, we have tested, let's say, both combinations. The longitudinal ventilation system, pushing the smoke downstream. Yeah, this has worked perfectly. So it means that the amount of smoke has been reduced, and the smoke, it was able to keep the tunnel upstream clear of smoke. Yeah, so we have two effects: the cooling of the smoke and reducing the amount of smoke in such a fire test. And we have seen in all cases that the water mist system was able to push the smoke downstream. As Tim already mentioned, for the Carey tunnel, we had also done the testing for the extraction of smoke. It had worked very well. In fact, there's a few systems which have been installed with water mist systems with smoke extraction, and the tests have shown that the extraction of the smoke has worked perfectly fine. Again, we are reducing the amount of smoke. Also in this case, we are reducing the volume of the smoke, and the ventilation system has been able to extract also the smoke into the duct completely. This is also the case we have seen in the Carey tunnel.
Yeah, and the wind speed stayed the same.
Wind speed stayed the same, absolutely. Yeah. So we want to thank you very much for listening to our webinar. We are very open and happy to receive your questions and feedback. You see the contact details on the screen. Please come back to us, and hope to see you soon in person for project discussion. Thank you very much.
Thank you.